Welcome to the second episode of Roses and Rivets. I'm Rose.
And I am Paul.
Welcome to the deep dive. Today we're getting into something pretty fundamental for how we build things here in New Zealand.
Yeah, we're looking at the standards for timber construction.
Exactly. Specifically, NZS AS1720.1.2022 and also NZS 3604 from 2011, plus its updates. Now look, these aren't exactly thrilling reads cover to cover.
Not exactly page turners, no,
Yeah.
but they are absolutely crucial. They're the foundation for safe, durable timber buildings.
They really are. Whether you're actually designing or building, or maybe you're just interested in, what holds your house up.
A basic grasp is pretty essential when you say. These standards set the bar for quality, for safety, right across the country.
Which brings us to you, listening in. We know you appreciate getting a good handle on important stuff without getting completely lost in the technical weeds.
Yeah, nobody wants that.
So our mission today, to pull out the key insights from these, pretty hefty documents. We'll touch on the timber itself, how it gets connected, structural stuff.
Yeah.
The big picture.
Trying to find those aha moments without drowning you in code references.
Exactly. Right, let's get into it. Starting with the actual material, the timber. What does NZS AS1720.1 say about that?
Okay, so it's quite specific. It lays out requirements for different grades. For example, if you've got visually graded sawn timber, it needs to meet NZS 3631 for what's called number 1 framing.
Okay.
Then there's mechanically graded timber that has to line up with the NZS 1748 series. And structural graded timber needs to conform to NZS 3622.
So you can't just grab any old piece of wood. There are definite quality levels testing involved.
Absolutely.
And something that jumped out at me reading through, these standards are really laser focused on the timber part, right?
Precisely. When you're joining timber pieces, the standard tells you how the wood should behave in that connection, but it doesn't automatically cover, say, the steel screws or bolts or plates you're using.
Or even concrete if that's involved.
Right. The strength of those non-timber elements, you got to check them against their own standards. Every single part of that connection needs to be up to scratch.
Makes sense. You don't want the screw failing, even if the wood is fine.
Okay, let's talk about sticking it all together. Fastener spacing, specifically screws, sounds like there's more to it than just winging it.
Oh, definitely not winging it. For screws, if you look at figures ZZ4.13 in the standard, the minimum distances are laid out. Generally, parallel to the grain, you need 10 times the screw diameter 10D.
10 times.
And also 10D in one perpendicular direction.
Okay.
But in the other perpendicular directions, it drops to 5 times the diameter, 5D.
Why the difference? 10 versus 5.
Well, the 10D parallel to the grain is mainly about stopping the wood splitting along the fibers. Wood is weakest there. Going across the grain, it's stronger against splitting, so you can often get away with 5D.
Oh, okay, so it's physics, basically.
Pretty much. Now, there's an exception mentioned for things like plywood and cross-banded LVL that's laminated veneer lumber.
Right, engineered wood.
Yeah, that stuff is designed to resist splitting much better. So for those, you typically follow the manufacturer's recommendations, which might allow closer spacing. Okay, so these numbers aren't arbitrary. They're about preventing wood failure around the fastener. What about bigger things, like bolts or dowels?
Similar principles apply. For bolts and dowels, especially when they're loaded parallel to the grain, so pulling along the length of the timber figure, ZZ 4.17 gives the rules.
Okay.
Spacing within a row of bolts, that's A1, needs to be at least 4 times the diameter, 4D. The gap between rows, A2, should be 3D or more.
And the ends. I imagine that's critical.
Very. The distance from the end of the timber to the first bolt, if that end is taking loads pulling away, that's A3T. It has to be the bigger value of either 5D or 50 millimeter.
Or 50 mils, okay.
But if that end isn't really loaded in tension, maybe it's bearing against something, that's A3C, and it only needs to be the greater of 4D or 50 millimeter.
So more wood needed if you're pulling on the end.
Exactly. It's all about preventing end splitting or tear out, basically the bolt ripping out the end of the timber member. You need enough meat there.
Makes total sense. You also mentioned rivets, briefly.
Yeah, the rivets are often used when you're connecting timber using steel plates. The main thing there is the rivet's diameter shouldn't be bigger than the dowel or bolt diameter it's being used with. Keeps things balanced, prevents overloading the timber around the rivet.
Got it. Okay, so we've talked placement, but how do the standards guide the actual engineering design of these timber connections?
Well, NZS AS1720.1 gives quite specific design rules. It covers small fasteners like nails and screws and larger ones like bolts, and importantly, how the timber member itself behaves in that joint.
Right.
And a really key concept, maybe a bit more technical, is this idea of the effective thickness of the wood particularly in steel to timber joints.
Active thickness. Okay, that sounds like we're getting into the finer points. What's that about?
It's about predicting how the wood might actually fail within the connection under load. The standard looks at it in two ways: elastic behavior and post-yield behavior.
Elastic meaning it springs back.
Exactly. If the wood is expected to deform elastically spring back when the loads remove the effective thickness, it's labeled T0FE or T90FE, depending on load direction. It's calculated using a factor CR from table ZZ4.11 multiplied by the timber thickness squared.
Square, okay.
And what's quite practical is if your exact timber size or bolt diameter isn't listed in that table, the standard actually lets you estimate by interpolating between values or even extrapolating carefully.
Huh. So even if your situation isn't perfectly standard, there's still guidance. What about when the wood doesn't spring back, post-yield?
Right, post-yield. That's when you expect some permanent deformation. The calculation for effective thickness there, T0 FEF or T90 FEF, it gets a bit more complex.
I bet.
It uses an equation involving things like and the number of shear planes in the joint, alpha I, the yield parameter reflecting how easily the wood starts to deform permanently, D, the dowel diameter, and F2 alpha, a characteristic embedded in the strength of the wood.
Okay, that's a mouthful.
It is. But essentially, this helps engineers predict how that wood will behave after it starts to yield, which is crucial for understanding the connection's ultimate capacity and ductility.
Right, so different models for different stress levels. Got it. Now, I notice a specific mention of naturally round timber. How's that treated compared to, regular square sawn stuff?
Good question. Table ZZ6.1 in the standard actually gives specific strength properties just for naturally round softwood timber in its unseasoned or green state.
They're for poles and things.
Exactly. And this is important if you cut sections from round logs, like maybe a half round or a quarter round shape.
Yeah.
You can't just use those round timber properties from table ZZ6.1. You have to go back to the general properties for timber sections in section 2.2 of the main standard, AS1720.1, but apply specific modifications found in Appendix ZZ2C.
Why the modification?
It accounts for the fact that the grain isn't perfectly straight relative to the cut faces anymore because of the original curve. So the shape matters for strength calculations.
Interesting. Okay, so you can't assume curved bits act like straight bits. Now, zooming out a bit, the standard talks about the ultimate limit state, ULS, and earthquakes. Sounds pretty vital for safety.
Absolutely critical. Any structure designed using this standard has to meet the ULS requirements from the loading standards, NZS1720.1, and the earthquake standard, NZS1170.5.
And what does that involve?
It means setting limits on how much the building can move or deform under extreme loads, like a big earthquake, and also limits on the strain the actual materials can take. The goal is survival preventing collapse.
Makes sense.
The standard also makes you think about deformation incompatibilities. What happens if different parts of the structure try to move in ways that clash during an earthquake?
And in NZ, earthquake design is obviously front and center. How does the standard approach that?
It uses this concept of capacity-protected elements, CPEs, and plastic deformation elements, PDEs, within the earthquake-resisting system.
CPEs and PDEs. Okay, break that down.
Think of CPEs as the really strong parts, designed to stay elastic, undamaged during the quake. They're protected. The PDEs, on the other hand, are like the designated fuses or crumple zones.
Ah, okay.
They're specifically designed connection points or members that are allowed to deform, plastically permanently bend, or yield in a controlled way. That absorbs the earthquake energy and protects the rest of the structure from catastrophic failure.
So you deliberately design specific parts to yield and soak up the energy. Clever. What about terms like yield displacement and ductility demand?
Right. The yield displacement of a PDE is basically how much it can move or deform before it starts yielding, before that permanent change begins. You can figure this out through analysis or by looking at connection test data outlined in section ZZ4.
And ductility demand.
That tells you how much more deformation that PDE needs to be able to handle beyond its yield point during the design-level earthquake before it actually fails. It's a measure of its ability to stretch or deform without breaking.
Gotcha. So how much give it has after it starts to yield? I also saw something about a dynamic magnification factor. What's that?
Yes. For simpler buildings, say, typically nominally ductile or limited ductility ones, 4 stories or less if you're using a simplified analysis method called the equivalent static method from NZS1720.1.
Yeah.
You can often just take this dynamic magnification factor as 1. Unity. It simplifies things.
Okay.
But for taller, more complex structures, you generally need a more sophisticated dynamic analysis to work out the appropriate factors. These account for how earthquake forces can get amplified at higher levels in the building, sort of like a whip cracking effect.
Right. More complex building, more complex analysis needed. Makes sense. Okay, let's shift gears slightly. Floor and roof diaphragms. What are they, and what does NZS AS1720.1 say?
Diaphragms are basically the flat planes, your floor sheeting, your roof sheeting.
Yeah.
They act like horizontal beams or girders spanning between the walls or frames.
And their job is?
Their main job is to collect lateral loads, like wind pressure or earthquake forces acting on the building face, and transfer those loads across to the vertical bracing elements, the walls designed to resist those forces. Section ZZ10 of the standard covers their design.
Okay.
For nice, regular, rectangular floor diaphragms, built with specific things like strong edge beams, cord beams, timber sheathing nailed down properly, timber joists, and importantly, solid blocking between the joists.
Yeah.
You can often use a simplified design method called the girder analogy. You basically treat the whole floor plate like a deep horizontal beam.
A girder analogy sounds like a handy shortcut for common floors.
It can be for those specific cases.
Mm-hmm.
But the standard warns against using this, or even more complex truss analogies, for diaphragms that don't have that solid blocking between joists.
Why not?
Because without the blocking, the way shear forces get transferred between the sheets of plywood or whatever is less certain, and the diaphragm might deform a lot more. You need a more careful analysis. Also, if you have loads applied directly to the edges, like wind hitting a wall that sits on the diaphragm edge, you need to make sure there's a clear path for that load to get into the diaphragm system. You can't just assume it works. It might need specific detailing or analysis.
Got it. Need to make sure those edge loads are properly handled. Now, our notes also mention the older standard, AS1720.1 from 2010, especially about modification factors and design capacity. What's that about?
Yeah, so the fundamental idea of calculating a timber member's design capacity involves taking its basic characteristic strength and then adjusting it using modification factors. This accounts for real-world conditions. This principle is in both standards, but the 2010 version has some tables often referenced.
And what sort of conditions do these factors adjust for?
A really big one is the duration of the load. That's factor K1 in table 2.3 of the 2010 standard. Timber can handle a much higher stress if it's only applied for a very short time, like a wind gust, compared to a load that's always there, like the weight of the roof itself. So when you look at different load combinations, dead load plus wind, dead load plus snow, etc., you use the K1 factor that corresponds to the shortest duration load in that specific combination.
Interesting. So the quick loads govern that factor. What other key factors are there?
There's K7, the length of bearing factor from table 2.6. It adjusts strength based on how much contact area there is where one member bears on another.
Okay.
And K9 is the strength sharing factor. This one's interesting. If you have several pieces of sawn timber acting together in parallel, like floor joists under common sheeting, and they can share the load between them,
Yeah.
you can slightly increase the calculated bending strength of each individual joist using K9. It recognizes that a single weak spot in one joist is less critical because its neighbors help out.
Ah, safety in numbers.
Kind of. But it's important to note this K9 factor doesn't apply to engineered wood products like plywood, GLT, glue laminated timber, or LVL. Their properties are already assumed to be more consistent.
Right. They're manufactured to be more uniform. Okay, so these factors fine-tune the strength calculations. Now, what about designing basic things like beams and columns using AS1720.1 2010?
Section 3 of that standard is where you find the rules for calculating the capacity of beams, columns, and tension members. It mostly focuses on members with simple rectangular cross-sections, like you see in Figure 3.1. If you have weird shapes, Appendix E gives some guidance.
Okay. And what if a member is doing two jobs at once, like being bent and compressed?
Exactly. The standard provides specific interaction equations for those combined actions. For combined bending and compression, like a column that's also getting pushed sideways, you have to satisfy equations 3.5 and 3.52. These actually account for how the compression load can make the bending effect worse.
Okay.
Similarly, if a member is being bent and pulled in tension at the same time, you use equations 3.53 and 3.54. These include a stability factor K12, which is important for working out the bending strengths part of the equation.
So these equations are essential to make sure the member is safe under combined stresses. Now, back to joints again. We did spacing, but what about the actual technique for putting in screws, bolts, coach screws, according to the 2010 standard?
Right, technique matters. For screws, AS1720.1 2010 really stresses the need for pre-boring or pre-drilling holes. To get the strength values listed in the tables, like 4.5A and B, the pilot hole for the smooth shank part of the screw should be the same diameter as the shank.
Okay.
And the pilot hole for the threaded part shouldn't be bigger than the root diameter, the skinny bit at the bottom of the threads.
To make sure the threads bite properly.
Exactly. Keeps it tight, prevents splitting. Although, interestingly, Appendix C notes an exception for plywood. Sometimes you don't need to pre-bore there.
What about bolts?
For standard steel bolts, M16 size or smaller meeting AS1111.1, you need to pre-drill the holes. And the holes should be slightly oversized, about 10% larger diameter than the bolt itself.
For tolerance.
Yeah, makes assembly easier. And crucially, you must use washers under both the bolt head and the nut, as specified in clause 4.4.5.
Right. Washers spread the load, stop the bolt head sinking into the wood, and coach screws. They look like beefy screws.
They are. Coach screws need to meet AS/NZS 1393. They also need pre-drilled pilot holes, and washers are mandatory again.
Okay.
There's also a rule that if you're joining two pieces, the thinner piece must be at least 3 times thicker than the coach screw's shank diameter.
To give it enough grip.
Right. And the hole tolerances are quite specific, too. The hole for the shank can't be smaller than the shank, but it also can't be more than 1 millimeter or 10% of the shank diameter larger, whichever is less.
Wow, precise.
It is. And like regular screws, the pilot hole for the threaded part shouldn't exceed the root diameter, and you need to drill it deeper than the length of thread you're screwing in. It's all about getting a solid, non-damaging connection.
Definitely sounds like precision matters for these connections. What about split ring fasteners? They pop up sometimes.
Yeah, split rings, they need to meet AS 1442. The 2010 standard has specific rules for their spacing too, laid out in clause 4.6.4.
Okay, so every fastener type has its own detailed playbook. Let's circle back to round timber again. The 2010 standard also has specific ways to calculate its strength, right?
It does. The design capacity in bending MD for a round timber member is calculated with a formula. It includes the strength reduction factor phi, the load duration factor K1, factors for temperature K4, and moisture K6.
Okay.
And, importantly, a factor called K20, the immaturity factor, plus the characteristic bending strength, way for prime, and the section modulus Z.
Immaturity factor, what's that about?
It basically acknowledges that timber from younger, faster-grown trees, especially near the center, but the pith, might not be as strong or dense as timber from more mature parts of a log. So K20 reduces the capacity accordingly for round sections.
Huh. Interesting adjustment. And shear capacity.
Similar formula for shear BD. Uses phi, K1, K4, K6, K20 again, but this time with the characteristic shear strength prime and the shear area A's.
Got it. So specific tweaks for round timber. What about glued laminated timber, GLT? That's a big one in engineered wood.
Absolutely. Table 7.1 in AS 1720.1 2010 is your go-to resource for GLT. It lists all the key characteristic values, strength in bending, tension, shear, compression, and also stiffness values like modulus of elasticity and modulus of rigidity.
For different grades?
Yes, for all the common GL grades like GL18, GL17, down to GL8. It lets engineers pick the right grade for the job based on the specific stresses and stiffness needed.
Super useful table. Now, thinking about how buildings perform over their lifetime, deflection, like sagging and long-term loads, must be important considerations.
Hugely important. Excessive vertical deflection, say in a lintel beam over a window or door, can cause the joinery to jam or even crack plaster.
Yeah, seen that happen.
And too much horizontal sway in the whole building could potentially damage neighboring structures if they're close by. So when you're designing, especially thinking about long-term effects like potential cracking or distortion, you absolutely have to consider the construction sequence, how loads are applied progressively, and also creep.
Creep.
Yeah, creep deformation. Timber, like many materials, will slowly deform over time, even under a constant sustained load. It's a gradual, permanent movement. You have to account for that long-term sagging.
So it's not just the initial load, but its effect over years. And Table B1 mentioned a link between deflection and end rotation for simple beams.
Yes, for a simple beam with a uniform load, there's a direct mathematical relationship between how much it sags in the middle and how much the ends rotate. That rotation can be important when designing the connections at the beam ends.
Okay. Now, a couple more concepts from the 2010 standard. Joint stiffness and proof testing. Sound a bit more advanced.
They are, a bit. Joint stiffness, often called KSEC, is basically just a measure of how stiff the connection is, how much load it takes to cause a certain amount of deformation. It's the design load Q divided by the resulting deformation delta O adjusted for load duration effects.
Okay.
But the standard makes a point. The equations we use to estimate that deformation. They're really best guesses for the first time the load is applied. If a joint sees repeated loading,
Like wind or traffic.
exactly, you need to consider that there might be some slip developing in the joint over time, and its stiffness might actually change. It might get sloppier.
Right, and proof testing.
Proof testing, covered in Appendix D, is basically a reality check. It's a way to physically test a completed structure, or maybe a specific component, to verify its strength. You apply a calculated equivalent test load, QE.
How's that calculated?
There's a formula involving various K factors and the design load. It's essentially applying a load significantly higher than the expected service load to prove the structure has an adequate safety margin. It confirms the design calculations hold up in the real world.
Like stress testing it. Okay, that covers a lot from NZS 1720.1, both new and old. Let's switch focus now to NZS 3604.2011 and its updates. This one seems more about the practical side of building typical timber houses.
That's exactly right. NZS 3604 is much more prescriptive. It's specifically aimed at the design and construction of relatively straightforward timber-framed buildings.
Like what sort of buildings?
Typically single or two-story houses. It sets limits on things like the maximum spans for joists and rafters, the overall building height, and it really only applies to common roof shapes, gable, hip, monopitch, or skillion.
So not for complex architectural designs or big commercial buildings.
Generally, no. It's primarily for domestic housing and some smaller residential buildings within defined size and occupancy limits. Large public assembly buildings, high-risk structures, they fall outside its scope and need specific engineering design, or SED.
SED.
And that's a key point. If your design deviates significantly from the specific rules laid out in 3604, or if you rely on manufacturer's details or products not explicitly referenced in 3604, then you can't just claim it complies. It automatically requires SED.
So it's a recipe book for common houses, but if you change the ingredients too much, you need a qualified chef and engineer to sign off.
That's a pretty good analogy, yeah.
What are some key terms NZS 3604 uses? It seems to have its own language.
It does. For instance, it defines a heavy roof that's one weighing over 20 kilograms per square meter, but not more than 60. Concrete tiles are the classic example.
Okay.
Heavy wall cladding is over 80 kilograms per square meter, up to 220 kilograms per square meter. Think brick veneer or stone cladding.
Right.
A load-bearing wall is simply any wall holding up vertical load from floors, ceilings, or the roof. And a wall bracing element is a specific section of wall above ground level that's designed and built to resist those lateral wind and earthquake forces. Getting these definitions right is key to using the standard correctly.
Helps categorize things properly. Now, fixings under 3604, I saw notes about wire dogs and nail capacities being updated.
Yeah, Figure 2.2 shows examples of wire dogs, basically strong steel wire ties used to hold timber members together, especially against uplift forces from wind trying to lift the roof off.
Makes sense.
And regarding nails, yes, the standard has evolved to recognize that nail guns are ubiquitous now. So where older versions might have focused on hand-driven nail sizes, the tables now often reference a common gun nail size, typically 90 by 3.15 millimeters.
Okay.
It usually also says that comparable hand-driven nails, like a 100 by 3.75 or a little by 4.0 millimeters, are generally acceptable substitutes if needed.
Good to know.
And more generally, for connectors, there's a formula provided. Capacity R equals phi times QI times N times K.
Oh, break that down.
Okay, phi is a capacity reduction factor for safety. Key is the characteristic strength of the fastener, often from testing. It's just the number of fasteners you're using. And K represents various other modification factors relevant to that specific connection.
So a way to calculate the strength of a group of fasteners. The standard's keeping up with modern tools then. What about the ground the building sits on? Does 3604 cover site requirements?
It does in Section 3. A big one is soil-bearing capacity. If the site doesn't meet the definition of good ground, which involves specific geological descriptions.
Like rock or very stiff soil.
Exactly. If it's not good ground, then the foundations must be specifically engineered, SED again. The standard also flags certain clay soils as expansive if their properties, like liquid limit or linear shrinkage, exceed set thresholds.
Because they swell and shrink with moisture changes.
Precisely. And to help check if you do have good ground, it mentions using the scalopenetrometer test as an indicator. You're generally looking for results suggesting an ultimate bearing capacity of at least 300 kPa.
So check the ground first, especially if it looks soft or is clay. Now, durability, huge issue in NZ's climate. How does 3604 handle that?
Section 4 is all about durability. It starts with determining the building's exposure zone using a map in Figure 4.2. This divides NZ into zones B, C, and D.
And Zone D is the harshest.
Generally, yes. It covers coastal areas, offshore islands, places with more salt spray and wind-driven rain. But you also need to consider local microclimates. Maybe your site is sheltered in Zone D or unusually exposed in Zone C.
Right, local conditions matter.
The standard absolutely requires that all timber components comply with NZS 3602 for preservative treatment level, based on their end use and expected moisture conditions in service.
So the right treatment for the job.
Yes, and it mandates separating timber framing from direct contact with concrete or masonry, usually with a dam-proof course or cavity. Table 4.1 is really important here too. It gives guidance on selecting durable steel fasteners, nails, screws, bolts, brackets.
What does it recommend?
It depends on the exposure zone and how sheltered the specific fixing is. It ranges from standard hot dip, galvanized for relatively sheltered spots in lower zones, right up to stainless steel for very exposed locations, especially in Zone D. You need the right metal protection to avoid corrosion.
Makes sense. Match the protection to the environment. Okay, let's move up to bracing how the house resists getting pushed over by wind or shaken by earthquakes.
Right, bracing design in 3D604 uses this system of bracing units, or BUs. It's a way of quantifying bracing capacity and demand.
Okay, how does it work?
For wind loads, the demand is worked out as BUs needed per meter of wall length. For earthquake loads, it's BUs needed per square meter floor area.
Is there a simple way to think about what a BU represents?
As a very rough rule of thumb, 1 kilonewton of lateral force is about 20 BUs, or 1 BU is roughly like resisting a 5 kilogram force, but that's very proximate. The actual bracing ratings for different wall linings, like plasterboard or plywood, are usually based on standardized testing, like the Brienzi P21 test method.
Okay, so tested capacities. How do you know how many BUs you need for wind?
It's a step-by-step process. You start with a wind region map, Figure 5.1, then you factor in the surrounding terrain roughness, the site's specific exposure, is it open or sheltered, and the local topography, is it on a hill or cliff. That leads you, via tables like 5.2 to 5.4, to a wind zone classification. Low, medium high, very high, or even extra high in specific areas. The higher the zone, the more BUs per meter you need.
And for earthquakes?
Earthquake bracing demand is also calculated, but it's heavily influenced by the site's subsoil classification. Sites classified as Class D, soft soils, or Class E, very soft soils, generally require significantly more bracing BUs per square meter than sites on rock or stiff soil.
Because the ground shaking is amplified on softer soils.
Exactly. So the required bracing comes from calculations based on these wind and earthquake demands, considering the ground conditions. Then you have to distribute enough wall elements with known BU ratings around the building plan to meet or exceed those demands.
Got it. It's a calculated balance. What about the foundations and the framing just above the subfloor area? What are the key rules there?
Section 6 covers foundations and subfloors. One rule is that bearers the main beams supporting floor joists or subfloor framing walls supporting load-bearing walls above must be positioned pretty much directly underneath, within 200 millimeter center to center.
To transfer the load directly?
Yes. The standard also sets maximum heights that different types of foundation piles, ordinary piles, cantilevered, anchor, brace piles, can extend above the cleared ground level.
Okay.
Concrete footings are generally needed under all piles, unless you're using driven timber piles. And that concrete needs a minimum strength of 17.5 MPa.
Right.
There are detailed figures, like 6.13 to 6.15, showing required sizes for concrete foundation wall footings, and rules about laterally supporting those walls. Interestingly, these concrete or masonry foundation walls can also be used as part of the subfloor bracing system, provided they meet minimum length requirements and don't have excessively large openings.
So they can do double duty. What about ventilation down there?
Crucial. The standard specifies minimum ventilation opening areas using vents in the foundation walls, or continuous slots or gaps to ensure airflow through the subfloor space. And it tells you when you need to lay a polythene damp-proof membrane over the ground surface under the house, usually when clearance is low or ventilation is restricted.
To control moisture from the ground? Good foundation, good ventilation key for longevity. What about the actual floors?
Section 7 covers floors. It includes rules for trimming joists, the joists around openings like stairwells. These often need to be doubled or use thicker timber, depending on the opening size and the span of the regular joists.
Right, reinforcing around holes.
Yes. And there are strict limits on where you can drill holes or cut notches in floor joists for services like plumbing or wiring. Generally restricted to the middle third of the span, certain distances from supports, and limits on the size of the hole notch relative to the joist depth to avoid weakening them too much.
Makes sense.
Table 7.3 gives minimum thicknesses for different types of timber strip flooring. If the floor is designed as a structural diaphragm, Figure 7.9 shows typical construction, and there are limits on the diaphragm's maximum length, usually 12 meters, and its aspect ratio, length versus width.
We talked about diaphragms earlier, and concrete floors.
Yes, it covers concrete slab on ground floors too. Specifies requirements for the damp-proof membrane, DPM, underneath types of material, how to lap joints, how to install it carefully around pipes, etc. It also briefly mentions shrinkage control joints, saw cuts, or formed joints put into the slab shortly after pouring to encourage cracking to happen in predictable lines as the concrete shrinks.
So lots of detail even in seemingly simple floor construction. Moving up to the walls.
Section 8 is all about walls. Bracing first.
Yep.
Wall bracing element ratings are given in BUs per meter, and the rating often depends on the aspect ratio of the bracing panel, length versus height. Table 8.1 gives ratings for concrete or masonry walls used as bracing. It specifies requirements for dragon ties at external corners, metal straps, or timber members tying the top plates of intersecting walls together. Then there's a lot on studs. Stud sizes and spacings for load-bearing walls depend on the wind zone and the loaded dimension, basically how much floor or roof area each stud is supporting. Tables 8.2, 14.3, and 8.2 cover this. Non-load-bearing walls have different stud requirements, usually lighter, covered in tables 8.3 and 8.4.
And lintels, beams over openings.
Huge part of it. Lintel sizes are determined based on the loaded dimension they support, roof, floor, or both, and the span of the opening. There are numerous tables for different situations like 8.11, A8.11, and others in sections 14, 15, 16. And importantly, especially in higher wind zones, there are specific requirements for tying lintels down against uplift forces. Table 8.14 and Figure 8.1 show how.
Need to stop the roof lifting off.
Exactly. Finally, the top plates of the walls need to be supported laterally to stop them buckling sideways between bracing lines. This support can come from the ceiling lining if it's fixed correctly, or from intersecting walls, or specific diagonal braces or connecting members. Longer stands of top plate need extra strengthening.
Walls are clearly doing a lot of work. What about posts? And then the roof structure itself.
Section 9 deals with posts relatively briefly. Table 9.1 gives uplift resistance requirements for their concrete footings. Figure 9.3 and Table 9.2 show acceptable ways to connect beams to the tops of posts.
Okay, and the roof?
Section 10 is roof framing, lots of tables here. Rafter spans and sizes are in tables 10.1, A10.1, and others in snow load sections. How to fix rafters to walls and ridge beams is in tables 10.14 and 10.15, A10.15. Ridge beam sizes themselves are in table 10.2.
What about supporting longer rafters?
You often need underpurlins partway down the rafter span. Figure 10.1 shows how struts supporting these underpurlins should be arranged. If the struts need to land between ceiling joists, you might need a stronger strutting beam, sized from table 10.7.
Okay.
Purlins themselves, the horizontal timbers running across the rafters that battens fixed, usually need lateral support from blocking between them.
Yeah.
Figure 10.2. And the standard guides selection of tile batten sizes. One key thing. If you're using prefabricated timber roof trusses.
Which is very common.
Yes. You must have a specific truss layout drawing from the manufacturer and a producer statement confirming they've been designed correctly for the specific loads on that building. NZS 3604 doesn't design the trusses themselves.
Right, relies on the truss specialist for that. What about ceilings? Do they get much mention?
Section 13 touches on ceilings, mainly in their role as diaphragms for distributing bracing forces at the top of the walls. Figure 13.3a shows limits on protrusions or cutouts in ceiling diaphragms. It also specifies the type of lining material, typically gypsum plasterboard sheets of a certain minimum thickness and density, fixed in a specific way to achieve the required bracing stiffness.
So the ceiling plays a structural role too. Now, I noticed specific sections for 3 kPa floor loads and snow loading. That's for tougher conditions.
Yeah, exactly. Standard domestic floor load design in 3604 is usually 1.5 or 2.0 kPa. Section 14 provides tables and adjustments needed if you have to design for a higher 3 kPa floor load, maybe for a crowded deck or assembly area. Similarly, Section 15 and Appendix A gives modified tables for member sizes and fixings if the building is in an area subject to significant snow loads like 1.5 or 2.0 kPa on the roof.
So the standard scales up for heavier loads.
Yes, higher loads generally mean bigger timber members, more fixings, maybe closer spacings.
And finally, there was a mention of plywood box beam lintels. a composite thing.
Yeah, Section 16 offers plywood box beams as an alternative to solid timber lintels, but only for supporting roofs that are not subject to snow loads. Figure 16.1 shows how they're made basically two flanges of timber with plywood webs glued and nailed to the sides. Table 16.1 gives allowable spans based on roof type and loaded dimension.
But not for heavy loads.
Right. If the lintel is supporting floor loads or walls above, or is in a snow load area, you can't use the Section 16 tables. It needs specific engineering design.
Wow, okay. That is a seriously comprehensive tour through two incredibly detailed standards. It's just so clear how everything links together, isn't it?
Absolutely. Material choices, how you fasten them, the overall structural concept, it's all interconnected in both NZS AS1720.1 and NZS 3604. You really can't look at one piece in isolation.
That's definitely a key takeaway. These standards build this whole framework where every little detail, from the timber grade to nail spacing, plays a part in the building's safety and durability.
Exactly. It's a holistic approach.
And it's also so obvious how vital it is to consider the New Zealand environment, the wind, earthquakes, the climate's effect on materials over time. NZS 3604 especially gives such a clear, prescriptive pathway for achieving that resilience in typical house construction.
It really does. It provides a valuable standardized method for the bulk of residential building, which helps ensure predictability and quality while keeping safety paramount.
So hopefully this deep dive has given you, our listener, a real sense of the depth in these standards without, getting totally swamped in every clause number.
Yeah, the goal was really just to shine a light on some of the most critical, maybe most interesting aspects. Give you a solid feel for the principles behind modern timber building practice here.
Right. And maybe just to leave you with something to chew on. Here's a thought. Given how detailed and, standardized timber construction is under these rules, how does that affect innovation?
Interesting question.
Yeah, what's the balance between having these really necessary prescriptive safety rules and allowing space for engineers and builders to come up with new, maybe more efficient or sustainable ways of doing things? Does it sometimes hold back ingenuity? What questions does that raise for you about how we'll build in the future?
That's a great point to ponder. Definitely something the industry grapples with as materials and techniques evolve. And look, for anyone whose interest has been sparked and you want the full detail on any specific area, we absolutely recommend getting hold of the full standards themselves and diving in deeper. They are the ultimate source after all.
Absolutely. Well, thanks for joining us for this deep dive into the world of timber standards. Until next time.